This is project 3 video number 2, the one in which we coded up. Let's see, get force, get that. I want to cook up a name for this. I'll call it function, and I think I have to return both mag and direction. I call the direction phi, so I think I'll just call this F, capital F for the magnitude of the force, and phi for the Greek letter phi, and equals, and dipole, it's the force of the magnetic field due to a dipole on another magnetic dipole. Mag dipole force. I know it's kind of a long name for it, but alright. Hopefully you can think of a better name. What did we need to give it? It was mu 1. I think I'll call it. And I'll go mu sub 1, comma mu sub 2. Yeah, it's just too long. Mu 1, comma mu 2. Tend to like to avoid the 1 because it could be mistaken for an L, but I think I'll go with it here. And then I believe it is x, comma y, comma theta. Make a quick check. Mu 1, mu 2, x, y, theta. Takes arguments mag dipole 1, mag dipole 2, x, y, theta. And let's get back to the function. Let's say, and that function, and I get the formula sheet out, and it looks like mu 0 is 4 pi times 10 to the minus 7th, and in our formulas we had mu 0 over 4 pi, which would just be 1 times 10 to the minus 7th, so I think I'd prefer to use that. So mu 0 by 4 pi, I'll call it, equals 1 times 10 to the minus 7th. Teslameters per ampere. Mu 0 by 4 pi. So that's mu 0 over 4 pi. And then I said I was going to say what R was. Let's A first. A, B, and R. So A is mu 0 by 4 pi times mu 1 times, I think I'll leave those spaces out, times mu 1 times mu 2. So look at that. I had it right there, times the cosine of theta. Theta is going to be given in degrees, so I'll use cosine d. Let's actually go to my code outline rather than looking at it directly. So here we are, and I do want to check. Yeah, theta is in degrees, so times the cosine of theta. And the other one's the same thing except for 3, and the cosine of theta gets replaced with a sine of theta. So times cosine, and then the d means in degrees of theta supplied by the user. And then B is pretty much the same thing, except that's a sign. And there's a 3 in there. 3 times. And we call it B. I think I might move that over so one can see how similar they are. Alright. R, the square root of x squared plus y squared. We set fx equals this expression. Memorize that. I've got it on a sheet of paper, so I'll read it off of there. A times, and then open parentheses, 9 times y, times y, divided by r to the 5th. And minus, I'm going to spread that out a little bit, 15 times x to the power of 3 divided by r to the power of 7. And then plus b times y divided by r to the 5th minus 5 times x squared times y divided by r to the 7th. Yeah, I don't like it being that spread out. Makes it harder to read rather than easier. So that part I'll leave. Matter of opinion, you can have it spread out if you like. I'm going to try copying this. Control C, Control V. Because FY was pretty similar, I think. So it's a Y where there was. Oh, and the first one I had an X. I think I may have copied down the B one, the F sub Y one. So 9x over r to the 5th, 15 x cubed over r to the 7th. Nope, that's good. And then this becomes x squared. And then times y. Okay. I have a preference to put the y first. Times y times x squared is for the second one. And then up here, b, 1 over r to the 5th minus 5x squared over r to the 7th, 5x squared y. So, yeah, I guess it doesn't matter. I'll put it more the way I had it in the paper, on the pencil and paper part. It's just, you have to recognize it does the squared first, so that's not like a 2 times y, but rather x squared, the quantity x squared all times y up there. And this has to be changed to an x, and then it's 5xy squared. And delete, and then y to the power of 2. And that looks good. This one, if I made that x squared times x, it would look the same as the one below it, but I think we're good there. So 5xy squared, along with that. And then f magnitude, what we're looking for, is equal to the square root of fx to the power of 2 plus fy to the power of 2. And then I think it's, let me check this a tan 2. I think I'll start typing it, see what happens there. That didn't help. I want phi equals a tan, ooh, that looks perfect, a tan 2 degrees, tan 2 degrees of fx comma fy. I want to just play around with that in the command window to make sure it is what I think it is. So to me, a tan 2d of 1 comma 1 should be 45 degrees. A tan 2d of minus 1 comma 1 should be 135 degrees, 90 plus 45 degrees. Let's see if I yeah, that one's surprising. So maybe it goes y comma x comma y. So yeah, I think I better look it up. Yeah, I'll try searching on. Let's see if the help works. Help a tan 2d. Yeah, so you put it y comma x, and it calculates that. Alright, so go to the editor. I'm glad I looked that up. Fy. So use Octave's built-in help there. A tan 2d. Unless I got help by the automatic pop-up window in the editor. But I think this is enough. Alright. And that means I gotta switch them around. So let's make sure that makes sense now. So I'm gonna try the minus 1 comma 1. Where I am, it's the x comma y, so I'm to the right and then down, so that would be minus 45, or you could call it 360 minus 45, which be like 315, but and plus I don't want help this time, I want the actual function. So that minus 45, if I go minus 1, minus 1. Alright, that's in the lower left quadrant So I'm expecting 180 plus 45 is 225 would be one way of looking at it. And if I went around the other way, 225 from 360, well, 220 from 360 would be 140, and then one more off of that, 135, and clockwise around. So yeah, it's working well, but you have to have it, the X come away in that order. Alrighty, I think that's probably traditionalist. So why they have it. So that should do it for the coding, and I think it's a good idea to play around with it, see if it makes sense based on our knowledge of how magnets work. So I'm going to try saving this. I'm going to copy that name, Control C, save, paste the name of the function. They got to be the same. Save, and there it is. This part, the root of the file name, so it's root.extension. The root of the file name has got to be the same as the function name. I got that. So let's try running it. I'll put, let's see, it's, I'll try to copy that again, and then I had 5 arguments. I'm going to try 1, 1, and then let's go maybe let's call it 6 centimeters away, 0.06, 0.06, and then add an angle of 85 degrees. So at least we get a number, and I need, by the way, I wanted to make sure if I run it with semicolon there, I get nothing. Also, I'm going to go force, angle, I'll call it force direction, equals, run it like that. Nothing shows up, but I have got things stored. And then I'm going to try it without the semicolon and see if that gives me both of those values. Yeah. Alright. So I'm going to put the magnet at a place where I expect attraction. So I'll leave those the same. I'm going to put it on the x-axis, 6 centimeters over. So this will be 0, and I'm going to put it 0. So this is to the right. Remember, we got a little bar magnet or magnetic dipole at the origin, pointing in the plus x direction. So it's like a little bar magnet with the north pole to the right from the point of view of when we're looking at a Cartesian coordinate system. And so now I've put another magnet to the right of that. So this one should experience a force to the left. So that would be, I call it 180 degrees. So let's try that. And if that doesn't work, then there was an awful lot of algebra there. There's probably some mistake in the algebra. So we did get 180 degrees. Now, so that did work. That's cool. Now I want to put it, I think I'll put it to the left of the origin, and again, it should be attractive. So the force, but it's the same distance to the left of the origin, same magnetic dipole strength, so we should get it in 0 degrees, I think. 0 degrees and same magnitude of force in newtons. Let's see how that works out for us. Hit enter. 0 degrees, same magnitude of force. That looks good. If you put 2 magnets side by side, they repel each other. essentially get a negative dot product, and so if you move it further away you get something that's a lower magnitude dot product but still negative, so in other words a little closer to 0. So, and I would expect it to be weaker than this end-to-end business, so let's try that, see if that is making sense. I'll put it just above it, so I'll put that at 0.06. I'm going to go same distance, and I got it pointing in the same direction as the other 1, 1. Seems like I don't have enough arguments there anymore. So it was 0, 0. Oh, I just wanted to change that to a 0 and I'll wipe it out. So 0, and then the y value is 0.06. 0.06 is the same thing as 0.06, but I'll take that out. And the angle's still 0, so it's pointing in the same direction, but I guess let me draw a picture of that. So the way I see it, what I meant to type in for this one is the original bar magnet is right here, North Pole, South Pole, and I just put one up here. So I'd already tried here and here. Things seem to be practical. Now here, I should actually get repulsion if they're facing in the same direction. And but I expect it to be weaker. I think the strongest force is when they're both on the same line there. Alright, let's check that. And I get the direction is 90 degrees, which would be repulsive. It's exactly what I want. The 90 degree, see, to the right is 0 degrees, this is 90 degrees, so this is the direction of the force. And then let's compare the magnitude at 0.06. So I'm surprised that it's actually stronger. It's saying it's stronger when they're side by side. Roughly 0.07 versus 0.05. So I think I'm going to assume I was wrong about which way it is stronger. So they repel more strongly when they're side by side like that than end to end. Oh, then they attracted, by the way. Let's I want to get back down on the axis. Oops. So I'm actually going to go, I think I'll go the old, well, that was the first one I tried. Then I got to something reasonable, so there. So let's try, I want it facing the other way on the axis. So 180. So now they're pointing toward each other, North Pole to North Pole. The centers are 0.06 meters apart, both on the x-axis, and we try that. And the force on the second one, which is to the right of the first one, is directed at 0, and it's the same magnitude. So I just flipped the magnet from the orientation in which they attracted to the orientation in which they repelled. So that's when I had the second one over here. But remember, 0 degrees would be to the right, and I got 180 degrees, so they're facing each other. The North Poles are facing each other. So it's making sense. I was a little surprised that the dipole-dipole interaction is so strong when they're side by side. I want to check the units. This is supposedly coming out in Tesla. So let's I think I'm going to do that with pencil and paper. I'll get back to you. Alright, I'm finding from our expression for A, I think we can see it up here. A, the units from the formula sheet, mu0 has units of Tesla meter per ampere, Tesla meter per ampere, and then the dipole, it's meters times I think it's amperes times meters squared. So amperes times meters squared, and then times amperes per meter squared times the other one, the mu1 times mu2. Cosine of theta is unitless, so one of the amps cancels out. So A and B both have units of Tesla amperes meters to the fifth. Alright, then when we put that in here for any one of them, each one of these things in parentheses has units of 1 over meters to the fourth. So if I multiply that by 1 over meters to the fourth, so that was A, and then times 1 over meters to the fourth, I've got the units presumably of force, and it comes out to be Tesla. What I actually have up here is Tesla amperes times meters. Well, if you look at the formula for current carrying conductor, the force on a wire in a magnetic field, it's I times L cross B, which is telling you that the Tesla meter ampere is a Newton. And so, sure enough, our units for Fx and Fy work out to be newtons. So our units are good. Where I know the way it should be, it works out. I'm a little surprised about the side-by-side, so I'd say I learned something from this little bit of code. Is my take on it, that the force was greater when the two magnets were side by side at a separation of 6 centimeters than when they were end to end at a separation of 6 centimeters. But it's repulsive that way too. So I think I've actually got it coded up here, and nothing left to do but the documentation and the finishing touches. I do remember one of the important things is it doesn't print anything at all if you use it with a semicolon. And then I wanted to see what the outputs were most of the time, so that was the force and that was the direction. So seems to be working. The units work out, and I'm convinced that I got a strong likelihood of it being perfect. There was some symmetry between the Fx and Fy, which was also indicating that things were right. So I'm going to call this a wrap on Project 3 video number 2.